So I want to talk about, well, so maybe before I get on that, I'm Max Kuhn. I work for RStudio. My job and the job of the people who work for me is to basically make various types of modeling easier in R. It's usually not that hard to do things, but we're really working to make sure that various types of models are easy to use for users, especially users who are relatively new to R and so on. So I want to talk today about creating like lots of models, so situations where you might be in, and this might not be all that common depending on what you do and the types of data you work with, but there are some situations where you need to fit a variety of different models, like a lot of them. And so we have a package that will facilitate that. I will be talking quite a bit about the tidymodels infrastructure. So you may not have ever seen it before. If not, I think you'll get the gist of what we're doing in the presentation, but the two best places to get help would be tidymodels.org. We spent quite a bit of time, especially on the Get Started pages and getting people like up and running with tidymodels. And then Julie and I are writing a book. Julie Silge and I are writing a book on tidymodels. It's about like 80% done. So you can see it there. So if you're into more long form documentation, the book would probably be better for you. The tidymodels.org, it's a lot like we have coordinated vignettes. You can think of it as like that. It's not like just random vignettes on random stuff. There's a method to the madness there, but it's shorter form compared to the book. So I want to talk a little bit about tidymodels in terms of like the sort of the main building blocks, the main types of objects and things that you would create in the process of building a model. As you'll see in a minute, like I will have a little bit of focus on like predictive or machine learning type models, but there's certainly an example at the end that's more about like, not inference, but not so much about prediction. So in tidymodels, there's the idea of, right now, we think of when you go to create a model, the idea of something like a preprocessor and then a model being separate things. So a preprocessor might be something as simple as like a formula, like a standard R formula. So you've got like MT-cars and you have, MPG, tilde, dot, that kind of thing. A preprocessor could also be something more sophisticated. So you'll see recipes in a little bit if you've never seen it. And recipes are sort of like a mashup of dplyr and model.matrix. Recipes allows you to do simple things that model.matrix can't do, but also some quite sophisticated data analysis type things. So the idea of a recipe is it's like a series of steps you apply to your data to prepare it for modeling. And so a formula or a recipe might be good examples of preprocessors. And then once you've specified those about like what your data are, what the variables are that are outcomes, which are predictors and so on, you would feed that into a model. But we really take the idea that the model and the preprocessor are separate things, as you'll see in a little bit. And also I'll talk a little bit about more from the statistical methodology standpoint. It's both to consider both these activities and how they fit into sort of like your data analysis pipeline and the process of analyzing data. Now, one thing that we're not going to talk about, because to be honest, we haven't implemented it yet, is we also want to have like post processors added to that list. So you can imagine like doing some sort of feature engineering and putting your data into like a logistic regression model, and then maybe having a post processor that optimizes the cutoff of your, like the probability cutoff for your model to best, balance sensitivity and specificity. So there are things you would do post-modeling activity like calibration and so on. Those would also fit into the idea of what constitutes like a data analysis that's based on a model. We just haven't implemented them yet, so I'll just kind of skip over for now. So the main building blocks, like when you create models, is the models themselves, as you'll see in a little bit, are created using this package called parsnip. And the job of parsnip is to give you like one interface to like a wide number or a large number of different types of models. So really all the model definition parts happens inside of parsnip. And then the preprocessors, there's actually more than two here, but just as another example, the recipes package can be used to create like a pre-processing series of pre-processing steps. Or if you have your data is pretty simple and you don't need to do anything terribly complicated, a basic R formula sort of counts as a preprocessor that we support. So this just maybe conceptualize things by taking an example that's not terribly exotic. Let's say we have some predictors of the data and they're highly correlated. I'll have an example of that shortly, but we see this quite often in a lot of domains where you have different ways of measuring similar things. So back when I worked in drug discovery, I did a lot of computational chemistry work. And one thing we do in computational chemistry is we would take like a molecule, like a drug compound, and calculate things like its surface area, how many rings and bonds it has, and things like that. And surface area was highly correlated with a lot of other features that we would calculate from a model or from a molecule. So, or a compound might have multiple molecules. So the number of molecules tends to be correlated with the surface area, because as you add molecules, it gets bigger and so on. Also, the chemists had like 15 different ways of measuring surface area, and they were highly, highly correlated. So just as an example, there are situations where that you have different ways of measuring the same underlying phenomenon, and that results in a bunch of columns in your data being highly correlated. Now, that might be a problem. So if you're fitting a linear model, you have to worry about collinearity and things like that. So we might want to have ways to address correlation. And one thing you can do, this kind of the classical way of handling it, is to use principal component analysis to sort of decorrelate your data. And so you would take the highly correlated predictors, run them through a principal component analysis function, and get the component scores, which capture like the same amount of data, but are uncorrelated. So you can basically decorrelate your predictors by translating them into these things called principal components. And in the literature, that's known as principal component regression. But it being the day and age we are, we have to have a better name for things. So, in the computer science, I think it's probably a better name called feature extraction, where you're going to take the features of your data and extract the relevant information into another format that is maybe perhaps better for the model that you're trying to fit. So, the question here is like, well, if we were saying like, what's our estimator here? Or the estimation parts of this like preprocessor and model combination I just described, like where do we think that is? Like what part of the process here is about parameter estimation? And so, here's a little diagram. We have our data coming in. We have formula, you could call that a preprocessor, but just some specification of the outcome is this column and our predictors are these columns. And then you put that through principal component analysis. And then you think about like least squares estimation if we're using like LM, and then that yields a fitted model. And so then the question is like, well, what are we going to call the estimation bit? Is it just, the least squares estimate from our regression? And that's one way of looking at it. A broader, more holistic approach is actually, this is the estimation part, that when you're creating your principal components, you're using the singular value decomposition, but that's a statistical estimate, right? We're taking data and summarizing it in a fairly complex way, but we're estimating parameters in sort of a preprocessor model or preprocessor algorithm, and that involves various calculations that constitute estimation. So the important bit I want to get at here is it sometimes can be really easy to not think of parts of our data analysis processes being like things that we're estimating stuff in. So if you think about just like centering and scaling your data, right, getting it all in the same units, like you're calculating means and standard deviations from your training set, that's estimation, right? It's pretty bland estimation, and it's not going to change the model that much in terms of like improving the model. But at the same time, you are calculating statistics, and then those should be thought of in the same vein as the calculations and statistics you use to estimate slopes and intercepts from like a linear model. So like, what's the difference? Like, okay, well, that's a nice conceptual thing that you just said there. Like, why do we care about that? Well, there's lots of examples in the literature of only thinking about the model as the estimation part. And things can go really, really wrong depending on what you're doing. So for example, if you don't treat the principal component analysis as part of the estimation process, you're kind of saying like, well, those are known things with no variance. Like there's no variability to those things. And by doing that, little typo there, by treating the PCA parts as known, you can sometimes really underestimate performance of your model because you haven't propagated the error that you get from PCA estimation into the model performance estimates. A really great example of this was, back in the, this was probably like around the year 2000, is there was a great paper that used support vector machines and basically backward selection, which they called recursive feature elimination. And they took some really high dimensional data and said like, wow, we can use like feature selection to get 0 errors in our data. And they cross-validated their model and things like that, but they didn't include the cross-validation. Inside the cross-validation, they didn't do the feature selection. So they would like select some features and cross-validate that model, and then get rid of a few more features and cross-validate that model. And because that feature selection part is a really, really powerful and important estimation process, they were vastly more optimistic about their performance than they should have been. And in fact, another paper came out shortly after that that recognized that problem. And what they did is they took the same software and the same data, and they showed if they just scrambled the outcome, so where the model should not be informative at all, they could still achieve 0 errors because of the selection bias that occurs by not including feature selection inside of cross-validation. And then another thing that happens periodically, and it sometimes is, you may not realize it's even happening, is this idea of information leakage, where you're taking data that is not part of the model training process and having that come into your predictions and things like that. So like accidentally using the test set or other data that are not your training set. So if you treat these estimation bits, or you don't treat the preprocessor, for example, as estimation, information could lead again to like, a bad estimate of performance. Now, again, if you're centering and scaling, like, it's actually not that big of a deal, if you ignore that as the estimation part. But if you're doing something like feature extraction or feature selection, or even something like imputation, these are things that have like a potentially large impact on the model. And so not handling them in the right way could lead you down the wrong path. So I want to talk about the model workflow. And so, I talked to you about preprocessors and model objects, and I showed you like recipes and parsnip package, hexes. What a model workflow does is it's an object that combines your preprocessor and your model object. And so you'll see an example in a minute, but why would you want to do that? And there's 2 reasons. One's methodological and one's organizational. So, if you have a new data set, you might be trying various combinations of like feature selection or feature engineering routines to get your data more effective in your model. And you might be trying different models. So, if you think about like, I tried this initial model, and while, I'm trying to predict, sale prices in Ames, Iowa or whatnot, you might find like, oh yeah, this one neighborhood does really poorly in terms of prediction. So you might look at your results and then go back and try another preprocessor that has features that compensate for that problem. And so now you have a sequence of preprocessors. And let's say every time you have different features that you think of, you might try that in like 4 or 5 or 6 different models. And before you know it, you've got like, 6 recipe objects and 4 model fits or more. And then you're like, wait, which one of those was the one that worked? So the nice thing about a workflow object in tidymodels is by bundling these things together, you can make sure that you always have them, which ones are coupled together, and the API is a little bit easier to use. So from an organizational standpoint, it's a nice way to just keep track of your work. But another sort of methodological benefit is you can't accidentally treat the preprocessor as outside the estimation process. So a workflow, it encapsulates all of the estimation bits the same way because you've combined the objects for preprocessing and modeling. So you just can't estimate the model and accidentally treat the preprocessor as something that just exists without any variation in it. So here's some code. So let me just walk through what we're doing here. So there's the tidymodels meta package sort of loads a variety of different tidyverse and tidymodels packages like dplyr and ggplot and parsnip and so on. We have some data that I'll use as an example. I've used it quite a bit, where it's ridership of the L trains in Chicago. So what we're trying to do is we're trying to predict ridership at the Clark and Lake Station in downtown Chicago as a function of features like the other station data lagged 2 weeks beforehand. There's some weather data in there, date, it's daily data, so we have the date and so on. So what we initially do is we split our data into training and test. So there's an initial split function in our sample that will do like a 3/4 of your data into training and tests. By default, you can change the proportion. And then these like little accessor functions give you 2 data frames back for the training set and the test set. So then in Parsnip, what you do is you design like what type of model you want to fit. So for these data, linear model works pretty well. We'll just keep it simple and say, let's fit a model using LM. So by saying linear reg in the first part of that call, you're saying, well, my model is one of linear regression, where we have a numeric outcome, predictors that are combined linearly with slopes, intercepts. And then the set engine bit specifies how you want to fit the model. So LM just uses ordinary least squares. If you want to do like regularized regression, you could use GlimNet or another engine. If you want to do Bayesian analysis, you can set an engine to be Stan and have it estimate it using Bayesian methods and so on. But that specification there just says it's basically a wrapper around LM. Now the next bit is a little bit more complicated, where this is a recipe. And the recipe, the initial call, by giving it a formula, we're saying, well, ridership is our outcome and everything else is a predictor, and our initial set of data is in this data frame. And then you see a bunch of like step functions that are sort of piped into that recipe. And the step functions are basically like data processing operations. So for these data, since they're daily, the most important predictor is date. So for example, if you use the step date function and give it a date column, what it does is it basically takes that day, or the date column, and adds additional features for certain aspects of the date, like the day of the week, the month, and the year in this case. Now for these data, a lot more people ride the L during the week than they do on the weekend. So that day of the week predictor is probably the strongest thing in our data set. And this is just like a simple, like high-level API to generate features based on dates. There's other things you can add here, like quarter and so on. Now, another thing about these data is when there's a holiday, less people ride the train. So for example, we have a step function that's step holiday, and then it has an automatic list of indicators it makes for various holidays in the US or outside the US. So for example, by using step holiday, what that will do is that will add new indicator columns for, let's say, Christmas and Thanksgiving and the 4th of July and so on, because we know those things have an impact on our model. They're important features to have. Now, there's nothing like terribly exotic about these two things, right? You could use like Lubridate or whatever to create them. But what we want to do is we want to have the recipe enable you to do things like in like a single call to a single piped object, where we can just make our code easier to use rather than having some script that runs ahead of the model that does these calculations separately each time. Now date's still in the model, but we probably don't want to keep it as a predictor. So it'll just get converted to a numeric for our model. So what we can do is we can give it a new role, and that new role could be basically anything, and I'll just call it ID here. And what that will do is it'll keep it in our data frame, but when we give it to these data to the model, it knows that that date column is not a predictor. So it stays in the data frame, but it's not exposed to the model as a predictor. And it's nice for plotting and things like that when you want to figure out, well, what's this large residual oriented, or what's this large residual signify? Like what day was that? And so having that date still hanging around but not using the model can be really helpful. Now, one thing we're going to do is, since we have a day of the week as a factor, we need to convert that factor into dummy variables so it can work with LM. So there's a step dummy. So what this code does is all nominal predictors it's very similar like a dplyr selector, like starts with or contains. But what it does, it says of the predictors, give me the ones that are not numeric. So nominal here signifies factor or character data. So in this case, we're selecting, one or more columns from our data to create dummy variables without actually giving it the names of those columns. We can select them by their role or their data type. And similarly, if we want to center and scale the data before running PCA on them, we can take all the numeric predictors, and what step normalize does is it calculates their means and standard deviations from the training set, and then we'll use those to put them on the same scale by subtracting that column's mean and dividing by that column's standard deviation. And then finally, let's do feature extraction. We'll take the columns that correspond to stations. So this vector of column names gets loaded when you load the data. And so what we're saying here is we know those station data are highly correlated. So if one station has a lot of riders on one day, the other stations, generally speaking, have a high ridership also. And the minimum correlation between these stations is like 0.88 or something like that. It's in the slides later. So it would maybe behoove us to convert those to principal components. So this selector is like a dplyr selector that says, do that calculation on just these columns of the data. And just for kicks, we'll say, let's keep 10 of those components. Okay, so this is our preprocessor, this is our model. And then to combine them in a workflow, we just basically start the workflow function, and then we can add a model to it and add a recipe, and those are bundled together here. So that was a lot of work to get there, but now we can go on. So the difference between what I want to show on the next slide is the potential methodology error that people can make. And you might look at this code and be like, well, who would do that? And my answer would be surprisingly, a lot of people maybe would do that. So one thing you might do is you might treat this recipe as just well, it's like a data pre-processing step. So how about I run this on all of my data and then split it into training and test? So for example, you might do all the estimation parts on this using the entire Chicago data set instead of just a training set. And that's what this code does. The prep function does all the estimation parts, the centering and scaling, the dummy variables, the PCA calculations. And then the bake function basically just gets that data out of the recipe. So modeling data here would be a data frame that has the holiday indicators, all the dummy variables, the principal components, and so on. And then what we could do is we could just give that data to the model. We could take the training set bits and give it to the model, and then make predictions on our test set. And it might be an accident that we realize that actually the rows here are inside of this larger data frame. So this is a good example of information leakage, that if you treat the PCA as just it's like computing a square or something like that, there's no uncertainty or estimation there, then your predictions here are going to be overly optimistic because you've used the same data to both fit the model and evaluate the model, which is problematic. Now, a better thing to do would just be the fit function on the workflow using the training set. And that will make sure that the training set is the one used to process the recipe, and then those data are fed into the model as opposed to accidentally feeding a larger set of data to the model. And then as a really simple API. So these two lines are a better version of these 5 lines here. So not only is it better from a methodology standpoint, but the API is much more simple to use than this other API. So maybe I'll stop there if anybody has questions so far.
Yeah, feel free to unmute if you have a question. I'm so sorry, I don't think I can turn on the chat today, and apologize for that. Anyone has any questions?
Yeah, I have a couple. Could you back up to this one slide before?
Yes, this one.
First of all, thank you for doing this. It's very, very wonderful you're doing this.
No problem.
And so I'm imagining that every time I want to do a workflow, I'm going to specify, as you say, the pre-processing, and I'm going to specify then the model.
Mm-hmm.
What I was thinking from the title of your wonderful presentation is that imagine, and maybe you're coming to this, that I have one outcome and a set of predictors, and maybe even the same sort of pre-processing. And I understand it involves estimation as well. But now I want to try, a logistic model, a tree model, boosting model, random forest model, all in the same data, and I want to know which model is best. And I'm wondering if this is what you're having in mind as you're proceeding here. Maybe I'm getting ahead of where you are.
We're going to get to that exact use case in a little bit. I don't know if that came through. So yes, that's exactly where this is going.
Thank you.
Okay.
Any other questions? If not, we can proceed. And yeah.
Okay. So, you can imagine like this is maybe what the question was like. You're starting with a new data set and you don't really know what's going to work or what's not going to work. You might have an idea what the features are, but you might realize that, well, I might need to add features sequentially because I don't know what might be a good idea or might be a bad idea. And so in the Chicago data, we have a good sort of sequential example of like model development that we illustrate for these data, so that the slides will be available, but it's an example where we say, oh, we just started off with the lag predictors and that worked pretty well. Well, once we looked at the residuals, we realized, oh, right, day of the week, really important. And then once we did that, we looked at the residuals and said, well, oh, wow, we're really missing some. Which are those? And those were the holidays. And you can see where this is going, that, as you sequentially do things, you're not really sure, like, if you knew the answer, you wouldn't have to do the modeling parts. And you might not know what model is best. So, as an example, there's a bunch of different ways to deal with this correlation between the predictors. So you might use PCA like we did. PLS is something called partial least squares, which is sort of like a supervised version of PCA. So it also comes up with new components based on the original data, but unlike PCA, the PLS components consider the outcome. So those might be more predictive and have the same similar like properties of the PCA components. So you might like do feature extraction using PCA or PLS. Another thing you might do is you just might do some filtering. So you might say like, give me the minimum subset of predictors such that the pairwise correlations are below like, I don't know, 0.9 or 0.95, maybe weed out the really worst offenders in terms of correlation and see if that like solves the problem. Or you could do like no sort of like pre-processing steps and use like a regularized model like LimNet or something like that. So you can imagine just for this one particular problem, you can envision like, a variety of things you might do. You're not sure which one's best. And instead of like just typing, submitting to R, waiting, and so on, you might want to do these things all simultaneously. And that's the idea of a workflow set. It's a set of workflows that do different approaches to fitting data to the same, or fitting models to the same data. So when would you use it? Again, it's good when you're starting from scratch and you need to fit or even tune a lot of models. I have a really good example, I think, for like variable selection, but like seeing sort of scaling up like something similar to like a likelihood ratio test, where we want to know what terms of our model are having the biggest effect, almost like a model explainer. So you'll see that at the end. Now, how often are we in this situation where we're fitting like a lot of different models? I'd say, I don't know, maybe, like for me, it was always like maybe 10 to 20% of the time, where I was really starting from scratch on problems that were not well defined. So, when I worked as somebody who did like predictive modeling for a living, you have, your boss or whoever gives you a new data set and you're like, all right, I need to predict this. And then you spend a lot of time learning about the data and then try, my approach is, maybe it wasn't a surprise, is to throw a really wide variety of techniques at it to see really what does best, and then figure out which of those is, the best for deployment and so on. I was really hesitant to create this package because I think there was high potential for like misuse. And I don't mean like deliberate misuse, but I worry about overfitting, that if you try, just in the extreme, if you try 1 million models, the one that fits best might not be actually best because you've tried so many things. It's like an overfitting problem. And so, in developing this package, it was really for a fairly narrow band of problems. And I wanted to make sure it wasn't sort of like auto-think. Like, you know, I think when people were talking to me about wanting something like this, they wanted to just give it a data set and it do every possible thing and spit out a model fit at the end without really any them touching the process at all. And I can see how people would want that, but I'm very, very hesitant to do that. So, you know, we had to spend some time designing this package so you have ability, like checkpoints, like where you look at things and say, okay, you know, now I should make decisions based on plots and tables about what works and what doesn't, rather than automating the selection of the model and so on. So you can do that, but we don't really like easily enable just like hitting one button and then 10 hours of computations later, you get something that is claiming to be the best possible thing for your data set. I think that's a really horribly bad idea. Although a lot of people want something like that. Now, you know, there's this idea of like AutoML, and we'll show you like something very similar to what H2O does for AutoML using workflow sets in another package. So you'll see a little bit of that. If you want to, you know, just purely base things on prediction, there are methodologically sound and disciplined ways of doing that. And so I'll show you one as an application here. But generally, the thing that stopped me from creating this package a long time is I was worried about people accidentally just hitting what I call like hitting a tack with a sledgehammer. Like you'll get the tack in the wall, which will break a bunch of other stuff in the process. And so I was very apprehensive at first about doing, but then I convinced myself that if we do it the right way, there's a use case that we have not fulfilled in tidymodels that this would solve. If anybody listens to the Not So Standard Deviations podcast, I sort of tagged them on the tweet about the meetup tonight because they saw this and spent a lot of time discussing it, and it made me realize that maybe in the documentation of the package we didn't really outline like, hey, well, here's where this would be like fit for purpose. You know, you don't need this. This isn't like the thing that everybody using tidymodels for any type of models would want to use. It's really for a specialized band of problems. All right, so what is a workflow set, right? It's like we're like, what, 16 slides in and I haven't really told you about this thing. Well, as you can maybe presume, it's a set of workflows. So what we can do is this workflow set package gives you a really nice API for creating a lot of workflows, like combinatorially creating workflows. And then we have really high level APIs that can do all the appropriate estimation, evaluate them using resampling, rank them, and figure out which is working and which are not, and let you sort of interrogate them more. So what we're going to do is we're going to create a couple different recipes, and we'll just use two models here, but you could easily see how this would scale up. So let me show you some similar code to what we did before. So here's our, you know, ordinary least squares linear model. Let's do something fancy like a neural network. You know, we don't know, you know, if we're going to use like weight decay, we don't really know how much to use or how many hidden units we should use or how long we should train it. So in tidymodels, what we can do is we can tune this model. So since we don't know what these things are, like we don't have a number to put in here yet, we can tag them with this function called tune. And that identifies them as things that we want to optimize. So the simplest thing we'll do here is just grid search, where we'll have like grids for all these models that have values, reasonable values for these tune parameters. And then we'll basically evaluate them using resampling to come up with what we think the best, like, you know, the best number of hidden units are, or how many iterations to train the model. So we don't know those right now, but one of the big things that workflow sets will do is optimize these along with all the other stuff. So here's our two models. Like one thing, actually, I didn't plan on doing this, but let me just show you. I mean, that's a fairly verbose model specification, right? So we had to type a lot here to get two models. And that's something we realized fairly early on. Let me just open a terminal here from what I was doing earlier. And I'll make the font bigger. So one thing that we did, let me start a new R window here. One thing that we added a few versions ago was in Parsnip. There's a Parsnip add-in now. And so it's an RStudio add-in that if you run this function, what you get is like a little module that comes up and it, oh, that's weird. It lists all the, let me make this, I think that's because the font is so big. Yeah. it lists all the, of all the packages you have loaded, it lists all the models that tidymodels will fit. So if you want to fit like a lot of them, and we're doing a regression problem here, so the list will change. We're not really, well, we are doing time series. So we could use like XGBoost ARIMA models, a bagged R-part model, a boosted tree using XGBoost, cubists, R-part, you know, we can, I'll just click on a bunch of stuff here, like, you know, like here's LM, and so on, nearest neighbors. What we can do is we can have it write out all those model specifications instead of us typing them out. Look at it. Oh no, that crashed. Wow, that was unfortunate. Yeah, so what it basically does is, let me go back to my slides here, is as you saw, when it doesn't crash, I'm using a development version, so that's probably what's going on, is if you don't want to type all this stuff out, we have like that add-in that will then, you know, you can click on 50 of them and add them in to your code blocks, pretty much ready to use, where it would write out pretty much this for you. Okay, so we have 2 models. We can do a lot more if we want. And then what are our preprocessors going to be? Well, we're going to stick to a recipe. I'm going to start off with an initial recipe that has like the fundamental things like dummy variables and the date features and normalization. And then one thing I'm going to do is I'm going to try PCA feature extraction. Now, we don't know how many components to save, so we can also tune that. So we can simultaneously tune and estimate our preprocessor parameters as well as our model parameters, which is nice. We can see if PLS would do better because that's like a supervised version of PCA. So we can take that same initial recipe and then just use a different step for PLS. We have to tell it what the outcome column is. And then we'll say we want to optimize this too. And then we could also do like a filtering step where we say, like, what's the threshold on how much correlation we're allowing between the predictors? We're not sure what that should be, so maybe tune that also. So we have like a basic recipe and then 3 different like, or 2 different feature extraction recipes and then 1 filtering. So we have 2 models and 4 preprocessors. And how could we go about fitting those fairly efficiently? And my dog is hacking it behind me, which must sound lovely. Okay, so that's what we want to do. So when we load the workflow set package, which comes in tidymodels, we just give it a named list of all these things. So, you know, basic features would be the simple PCA recipe, like the one for filtering, you know, it would be this recipe. And then we give it a list of models and we can give them any names that we want. And then basically it crosses them. So we have, you know, 4 of these and 2 of these. So we get basically a tibble that contains a bunch of workflows. So you get this back, it has like, you know, it concatenates the names here, like basic LM to get you basic LM. The workflow itself is embedded in here. And then I'll talk a little bit about these columns in a minute because they don't really get populated until you start doing stuff. But what this did is it basically just crossed these, did the little bit of code that like adds model, adds a recipe. And I should also say you can have a formula here. So I could like do tilde like ridership tilde dot, and that would just get included like it would anything else. So you can combine, not only can you combine different types of models, you can combine different sort of like classes of preprocessors here. And then it just, you don't have to do the Cartesian product, but it will basically by default do like an expand our grid thing and makes 8 recipes here. Now these are still untuned, right? So we have a bunch of tuning parameters. So we're going to want to do some things with these recipes. To do that, when we do model tuning, we tend to rely on resampling. And this is a time series data set. So I'm going to use this type of resampling called rolling forecast origin resampling. And I think there's like 16 years of data in here. I think that's what it is. What this specification does is it says, running the sliding period function, it says take this data set and base the periods on the date column. And I want to do things by month. So by saying look back equal 12 times 12, there's 12 years, of course, in a month. And what this will do is it'll take 12 years worth of months, and that will be like the first like model fitting data set. Now this is a rolling situation. So what it will do is the size of the training set will always be that big, but it will just start to like tile its way across time until it runs out of data. So it's like a training set that is 12 years long. And then this next little bit here says, make the assessment set or the data that's being used to evaluate the model and take the next subsequent month. So for every one of these resamples, I have 12 years worth of data, and then next month is used as the holdout set. And that sort of arrangement, there's more data than that. So it just sort of keeps moving along the entire data set to make. In this case, it's 43 different resamples. So we'll be fitting, for every model that we tune, we'll be fitting it separately to 40 different versions of our data, and then using the next month to measure performance each time. So it's kind of like, if you think about like 10-fold cross-validation, we have 10 resamples. This is sort of like 43-fold, but it's more of a time series structure than it is like how, let's say, cross-validation does things. So this generates a resampling object. And then if you've used tidymodels before, you've probably used the tune grid function. So what we can do is we can take our workflow set that we have here, it's called Chicago workflows, and then basically map across it like we would do with PER. And what we can do here is give it options of things to use. And by default, it uses grid search. So we use grid search to optimize the parameters. And then we just pass things in to what we would have given tune grid. So we give it the resamples, the size of the grid. So every separate model, we're going to let it choose 20 values of the grid points based on everything it knows about those types of parameters, using what's called a space filling design. And then we don't have to tell it what metrics to optimize. It has a set it does, but in this case, we'll just measure the root mean squared error of the models. So we're basically passing in arguments to tune grid, and those arguments will get applied to all of the workflows. Now, the one sort of oddball here is a seed argument. What we want to do is make sure our results are repeatable. So what setting the seed value does is it says, well, when you go to fit these 8 different workflows, reset the random number generator before you do that, so they all use the same random numbers as they go through, and this will make the results reproducible. Now, what this does is it will go through all 8. We'll go through all 8 workflows. It will fit models for 43 times 20 different combinations of data and tuning parameters. So it's fitting like a large number of models across 8 of these workflows. Now, the original workflow set you see here, which we showed earlier, has these 2 columns. One's called options or option, one's called result. The results of the tune grid calls will be placed in this list column. So, this will be a tune grid object for this particular workflow and so on. And then the options that we specified here, like resamples, grid, and metrics, those get captured in a list here for each one of the workflows. So in other words, we're capturing all the things that we did along the way. So if we want to reproduce the results here, we've set the seed, so we know what random numbers we've used, and we've captured the options that we gave to tune grid. So this is just all the bookkeeping to save the results and save all the elements that went into those results. There's also a verbose option here. I didn't show it in the slides, but one nice thing is you can see when it starts a workflow and when it stops it and the progress along the way. One other thing that I'm not showing here, but I do under the hood, is tune grid uses parallel processing. So, for fitting that neural network with, PCA feature extraction, we're going to do 20 different versions of that model across 43 resamples. And, and that's a lot of models. We can do those all in parallel using however many cores we have in our computer. So, so if you've used tune grid, you just use 4 each and set up your parallel backend. Plenty of documentation on tidymodels.org and in the package and in the book. But one thing I didn't really spend a lot of time on here is there's a whole lot of parallel processing that can happen to make this much, much more efficient than just sequentially. So we run this, again, it's going to plop a bunch of stuff into these columns here. And the results look like this. This is not really formatted correctly. I forgot and used the development version of one of the tidyverse packages. This actually has a little nicer print method when you use the CRAN version. But the important part here is we see that instead of this just being empty lists, we have like a little print method for each one of these. There were no tuning parameters for this model, so it's just a resampled object. The plus here means everything went well, like there were no errors. You'd see an X here if something failed. And then these objects are tuning objects from TuneGrid because all these other 7 workflows had parameters to optimize. So this is what you get back, and you might be like, well, that's wonderful, Max. Like, it's a bunch of list columns, and what do I do with that? And of course, like with tidymodels, we give you a lot of high-level APIs to interact with these things. So one thing you might do is you might say like, hey, rank these models for me. So there's a function called rank results. You can set select best equal true, and when you do that, it'll give you a row for each workflow. If I set this to false, then it would give you a row for every tuning parameter combination in each workflow. So that could be thousands of things. So what this first row says is the partial least square feature extraction combined with a neural network had the best results. The mean squared error here is 2.01. The next best was, so there's one of the tuning parameters inside this workflow that gave us these results. And then the next would be PLS with a linear model, and that did, almost as good. And then equivalent to that was PCA with a linear model and so on. So you can see sort of how these things shook out just really simply by running like one line. This line here just makes it easily fit on a page. So you really just need this one line to get an immediate assessment of how well these things did. Visually, you can use the Autoplot method. So if you run Autoplot, by default, it gives you all the results. Since resampling, it does 43 resamples, these confidence intervals are based on all the resampling statistics. And you can see they're colored by model. So, there were a lot of neural networks that did not do so great. And then you have some linear models that actually did pretty well, but the one that seemed to work best was we had just the right parameters for this particular neural network to sort of take the lead. It's not much better than these, but it was ranked highest. And this is the same one that was shown over here. So this is a nice visual display, but if you're fitting a lot of stuff, it's kind of like a bit much. So there's also a select best argument here. It says rank them the same way we did before, or show me the best, this one would be like the best PLS neural network combination with its confidence interval. So this line here is the same one here. It just happened to be the best of those. And that workflow has a bunch of other lines here that were in that assessment. So again, really easy ways to figure out what seems to be working. You have confidence intervals, so you can measure like, oh, well, is it worth it to use a neural network more than like a linear model? And so you can sort of make these judgments about like, well, this one, this one's best, but it might be more of a pain in the butt to use. Let's do linear so we can do more explainability statistics and so on. So again, you can work with like this object as much as you want using mutates and per maps and things like that. But for most of the things you would want, we have really high level functions to operate on these objects. So any other questions at that point about this? It's a good place to get an interim assessment of what you think.
Good work.
Yes, go ahead. See someone raise his hand.
Yeah, DG.
Yeah, you can just unmute. Yeah.
You have slanted grid. Slanted grid, I don't know how to describe it perfectly, but slanted grid, like if one of the parameters being tuned isn't really that important, but making sure that all of that the other parameter is much more thoroughly explored. Do you have such a feature?
Not precisely. I'll show you something in a minute and give you references for it, something called racing that might have the same, it's probably not the same thing, but it might get you to the same area. So like, if you had like 4 tuning parameters, but only one of them really mattered, like that might be what slanted grid does. I'm going to look that up. But we have other methods that would like concentrate on optimizing that parameter. Another thing that would fit that is we also have a bunch of sequential optimization things. So I'll show you this in a minute, but you can choose a different function to run instead of tune grid. So we have like Bayesian optimization methods, for example, and that would have the same effect of what you're talking about. Is it would, after a few iterations of looking for good tuning parameter values, it would tend to focus on optimizing the tuning parameters that it thinks empirically are most important. So it would have that same effect, but I don't know what slanted grid is. I'll Google it. It might have the same effect.
Thank you. I think that's all.
Yeah, if you want, like maybe put in an issue in workflowsets, and we could discuss it more, like with a reference or something. That would be very helpful.
William?
Hi. So I have a question about the set seed values. So for example, in your recipe, you had the PLS, which is a model in and of itself. And then you pass the output of PLS into neural net. So then you're kind of having a model in model.
Yeah.
So when you're doing the set seed value, is it resetting the seed value before the recipe and the estimator, or are you just setting the seed value right in the beginning of before you execute the recipe?
We're setting it once at the very beginning of all the data processing. So in this case, it would be right before the recipe, and then you use the stream of random numbers you get for that, like however many you consume. And then when you go to like the second workflow, it resets it again at the very start of that. So let's say you did like, let's say you had one workflow that used imputation that, I don't know, use random numbers or something, and also use a neural net. You wouldn't, the neural nets wouldn't be using the same random numbers each, but at least it would be, from a top level, would be reproducible.
Okay, I'm just wondering whether the cross-validation RMSEs are comparable if one recipe is supervised, but then the next recipe is unsupervised, because you have a PCA recipe and then you also have a PLS recipe.
Yes, that's an excellent question. So the thing that's happening, the really good question is like, well, your pre-processing is using the outcome, so how are you not overfitting? So to paraphrase you, hopefully I got that right. And so the idea would be, since we're doing the resampling, our data that was held out from that entire process would tell us if the pre-processing bits that are supervised are overfitting. So if they were, I mean, PLS is a linear method, so it's not really likely to overfit to begin with. But if we had any supervised bits that were in the recipe and they were really overfitting, the fact that we're always holding out a separate data set to measure performance on the entire workflow is our insurance policy to know that our assessment of those models are valid, because they're evaluated on all the same data, which was not used at all in the estimation process. Anybody else? Okay, good question. All right, so I wanted to show one. So at this point, like, I'll just show you a couple different things you can do with workflow sets. I think this kind of illustrates the idea that we're going to cross a bunch of stuff, combine them, and then just iterate over all this stuff, and then have ways of picking out like the wheat from the chaff. So here's a thing we might do is, I used this option of grid equal 20, and what the automated grid parts do here is you can give it a specific grid if you want to for each model. But when you just let it pick the 20 points, it doesn't know much about the data, right? So it doesn't know that the minimum correlation between these stations is like, over 0.8. And so what it does by default is it says, oh, well, that threshold bit for the filtering, that filter could be between 0 and 1. So I'm just going to give what's called a space filling design to fill up that space, whether I ask for 10 of them or 20 points. I'm going to like fill up that space in what I think is like a valid way. But most of that space doesn't matter to this problem because only values of like 0.88 and above have any effect on the model. So how would we customize, for example, the tuning parameter values that are used for the filtered models? So as an example, what we do is in tidymodels, we can get that workflow out by running this pull function. So we say, give me the workflow back from this object, and it's the one that corresponds to the filtered linear model. That gives us a workflow back. We can extract the tuning parameters that were given, that were set for that model, which in this case is just the threshold. And then we can update the range of that tuning parameter. So, the lowest correlation is 0.88. Let's like do 0.87 to 0.99. So this would get rid of almost all those predictors, and this would get rid of none of them. And then instead of it setting that space filling design to be between 0 and 1, it would set the space filling design to be between 0.87 and 0.99, right? So this is like adapting the right range for that parameter. And then we can do the same thing for the neural network. There's really not much of a difference here. The only thing to keep in mind is there's only one tuning parameter for this model, but there's 4 of them for this. So we're just going to update this one, and all the others like weight decay and hidden units and all that are set to their default ranges. And so now that we know how to specify the parameters, how we pass these in, because this is only relevant to one of those workflows out of 8, and this is relevant to another workflow out of 8. So how do we do that? The simplest thing you can do is there's an option called options add, and then you can pass in any options you want to as if you were using TuneGrid. So what this says is for the filtered LM workflow, set the tuning parameter info to be this object, and then do something similar for the neural network. And so this is just like updating the options. And you can see a little note here that says your options are being modified from what they originally were. And so we might want to just refit these two, because now we have different ranges and these might work better. And so a workflow set, to go back to this one plot, it's a tibble with an extra class. So we can use all the dplyr things that we normally do, like mutate and filter and select. So when I add those additional options in, what it does is it updates the things that are in this column and knows that these are the options that should now be reapplied when we run TuneGrid. So in this little sequence of things, I only want to refit these models, the ones that have filtered in them, because they're the only ones that have changed. And I just basically give it the same workflow map before. And then this just reruns those with the new tuning grids that I've specified here. So I don't need to rerun everything from scratch. And then what I can do is I can just recombine them. Is I could say, take the original results that I've already computed, get rid of the filtering ones because I'm going to replace them, and add the rows back in for the filtered. So these are the ones I just reran. So this gets rid of their original results, and this adds back in the results that are new. And so then we can just work with this object now. So, are rank results any different? Well, look at that. This was the best one before. When we adjusted the filtering range, we actually got slightly better performance by doing that. So we really, this was a good idea to do this. I mean, it's a small adjustment, but it's still, we're estimating on 43 data points. So it's probably, fairly significant. And then one final thing is there's when you run Autoplot, you can actually run Autoplot on a specific workflow result. So if I want to see what the tuning parameter results are for just this model, I get my typical plot I would get here, where you can see that, for this case, as the threshold increases, on average, root mean square goes up. So I think it tended to want a model with very low filtering. Like this is the filtering value it liked the most. But on average, it liked less filtering as opposed to more. It liked, a moderate number of hidden units. The number of iterations didn't really seem to matter, and it seemed to like a lot of regularization. So we might even, if we really wanted to, like up the amount of regularization and refit again based on that, if we really wanted to optimize more. But just as an example, Autoplot could be applied to the individual models like you would if it were with TuneGrid. So that's another thing that you could do. Now, after this, there are some sort of tie-ins to other packages that most of the tidymodels packages work together. So you might want to say to yourself, like, are these things statistically different? Well, it turns out there's some Bayesian methods you can do to use that, to answer that question. We have a package called tidyposterior. And if you give it the workflow set and set up the parameters around a Bayesian model, we can actually make inferences on the model-to-model comparisons. And so there's this one type of analysis you can do for Bayesian models called ROPE analysis. ROPE stands for region of practical equivalence. And it's like a subject-specific problem where if you use the units of your metric, which in this case was RMSE, we can basically try to use some Bayesian methods to answer, not are these things statistically different, but are they practically different based on some sort of like effect size. So the outcome data here are in thousands of rides. So if I say it's an effect size of 0.15, what I'm basically saying is an MSE that differentiates like 150 riders from one model to another, is that defines our practical like equivalence. So we're saying that if a model it gives me results that are larger than 150 root mean squared riders, like, riders, it's in units of riders, but for the root mean squared error, we would consider that a practical effect. But anything that's lower than that, we wouldn't really consider it. And so you can look at tidyposterior to see how it does that calculation. But when we run the autoplot on that, what we get is we get a probability of practical equivalence to see if any of these other workflows are practically equivalent to the best one. So this is our filtered neural network. The Bayesian model thinks the next best one was the partial least squares with neural net. And it has about like that's about like an 80% probability of being practically equivalent to the best model. And you can see like there's some that are about 75% probability of being equivalent, and then one that just has a very low probability of being just as good as this one. So it's a nice little analysis that does something a little bit more than statistical significance based on what you think is a big enough difference in the models based on the units that you're in. So that's a nice little thing you can do with workflow sets that I think is kind of a nice way to look at rankings. Because, somebody would say like, yeah, these things aren't really statistically significant, but the practical significant is saying like, how big of a difference on the units of this y-axis are important to me. And if they were like 150 riders, we would say that, the probability that these two things are equivalent is about 80% based on that. So that's a nice little feature. Another thing you can do is, I mentioned this racing idea, and there's links to this in our book. What racing methods do is they are adaptive, and they decide which tuning parameters they should really investigate and which ones they should throw out. So, for each one of these models, I did like a tuning grid that looked at 20 tuning value combinations. So what it would do is it would do a couple of resamples and estimate like means and standard deviations of the RMSE, kind of like we did for the Bayesian analysis. And if it finds that like one tuning parameter combination is really, really statistically significant than the best one, the probability of that bad one end up being good is very, very low. So what it does is, as the resamples are processed, it can basically say, oh, these don't really seem like they're doing well, I shouldn't bother resampling them. And so there's a couple of good examples of that in our book. What it does is it ends up doing fewer and fewer model fits, which means that things run faster and faster. So it's sort of like an adaptive way to explore your tuning parameter space, and it will concentrate in areas that it thinks based on initial results are best. And if you've ever heard of like interim analysis in clinical trials, it's not terribly different than that. It's saying like, this one parameter has no probability of being the best one, based on the math. Why should we continue resampling it? Because it's just costing us time. So it just sort of calls those tuning parameter values as it iterates through the resamples. Now, if you want to do that, there's really not much to change. The racing bits are in a package called fine tune, and there's a function called tune race and nova there's different types of racing methods, and we have one that's based on ANOVA statistics. And so instead of tune grid, if you give it this as the initial value, it says, well, do that, all those same computations, but use this function instead of tune grid. And this would enable you to do racing sort of on a large scale. And at the times I've tried this with a couple of different data sets, the speed up is about, I mean, it could be anywhere from like 4-fold to like 10 or 20-fold, depending on the data set and things like that. And they tend to produce almost the same, if not very similar tuning results than just doing the entire grid. So if you look at the help page of this, like I have an archive paper that does a bunch of simulations to show that how the racing here is implemented doesn't really cost you in model performance, because you can worry about, oh, well, the first couple of resamples indicate this one tuning parameter is bad, but if we'd gotten them all, that might have been the best one. And these methods do a pretty good job of excluding ones that are really, really unlikely to be the best. So that's a nice little thing. If you're fitting a lot of models, you can fit, far fewer models using these racing methods. So that's like a little bonus you get almost for free using workflow sets. And then an additional bonus is ensembles. So one way to ensemble models is something called stacking. It's actually kind of like the original ensembling model. Since you're in LA, there's some people at UCLA who are like experts at this. So I don't know, might be more popular there. We have a package called Stacks that enables model stacking. So what it would do is it would take all these different models that we've already fit and then figure out how to combine them into sort of like an ensemble. It's very, at a high level, similar to what random forest does, is you would get multiple predictions across multiple submodels from all your workflow sets, and would try to optimize which ones to keep so that you have a better ensemble prediction than using any one model. So this sort of AutoML approach is very similar to what H2O does, where they fit a bunch of different models and use the same sort of stacking algorithm that we use, which is actually not that hard to implement. There's a lot of details here at the Stacks package on site. I have a chapter I've written, it's in a pull request. So maybe in the next week or two, there'll be a chapter in the tidymodels book on this. It works pretty well, to be honest with you. It's not gonna, if your R squared is like 0.7, it's not gonna take it to 0.9. But if performance really matters to you, it might take it from like 0.7 to 0.75. So it'll give you real but incremental improvements to the overall prediction. That prediction will involve a lot of models, but again, if performance is really what you need, that might be a good way of doing it. And it's a way to not really worry about, if you don't want to worry about all the model tuning and choosing between models, you can just let the ensemble figure it out, and that's sort of the AutoML that is here. Yeah, the only other thing I'll say about this is, this was developed by an intern of ours last year, Simon, and he won the John Chambers Award last year for this package, which was quite a nice kudos. So it's a really well-designed package. The syntax is really simple. Like a workflow set, you just start with an empty stack. You add all the models to it that you want to include in the ensemble. And since they're all in a workflow set, you just give it the workflow set. This part figures out which models to keep and which ones to get rid of. And then you need to do some extra model fitting at the end so that all the models that you keep are fit on the entire training set. And that's what fit numbers does. So very, very concise syntax with a very well-defined problem. So it's a kind of a pleasure to use here. And then one last application of workflow sets that I'll use is one that's based on like variable assessment. So, I don't know if there's many statisticians here or people who've heard of the phrase likelihood ratio test. But the idea behind this is you have two models that are built on the same data. And let's say one has like 4 terms in it and the other has all but 1 term. So you have one model with 4 terms and another model with 3 terms. And it's just like missing one of the four. So the one with four would be called the full model, and the one with three would be called the reduced model. And what your standard ANOVA methods do is when you put those model into like the R's ANOVA method, what it does is it calculates basically the difference in the sums of squared error. Let's say it's a regression problem. It calculates the difference of the sums of squared error and say, well, is that difference large enough given the amount of things that I took out of the model? And then for linear regression, it uses like an F-test to figure out if that's statistically significant, and then it gives you your p-value. And so when we do ANOVA methods comparing two models, it basically does that. It takes like a full model and a smaller model and figures out if the difference in performance is worth it, basically based on the degrees of freedom that you free up by doing the smaller model. We can do something similar in concept. What we can do is we can create a model formula and then create a sequence of subsets of those formula that leave one predictor out at a time. So for example, if I load this biomass data, it has like 5 predictors, and it's a linear regression problem. So if I take that and give it basically a formula where I'm going to model main effects and 2-factor interactions, if I take that formula and give it to this workflowsets function called leave var out formulas, what it does is it will produce a list of 16 formulas. One is the full model, like everything in it. And then here's an example of the formula that leaves oxygen out. So there's like carbon, hydrogen, nitrogen, sulfur, and oxygen. You can see all the two-way interactions are included, but none of these include oxygen. So the full model would have a main effect to oxygen and like 5 additional two-way interactions that involve oxygen and the other predictors. And so what this function does is it gets rid of any model term that involves that particular variable. And so why would we do this is what we can do is we can take all of those model terms and one by one remove them from the model and figure out if the change of performance is big. And if it is big, then we know that, oh, that should have been kept in the model. And you'll see what I mean by this in a minute. So it's a way of comparing like a full model and a reduced model. Now you might say like, well, Max, why would I do it this way? I have ANOVA and I can just do this. Well, the difference is ANOVA is based on, let's say for linear regression, it's based on like sums of squared error. So what we can do with workflowsets is we can do that sort of full and reduced model comparison using any model or any metric that we want to. So if we were doing logistic regression and want to do that sort of likelihood ratio type comparison, but base it on, let's say, the area under the RC curve, you can't really do that with the standard theory. So what we're going to do here is we're going to use bootstrapping to get bootstrap estimates of that difference when you take these model terms out and see which ones are equal to 0 and which ones are not. So let's do that. So again, we have this list here that has 16 elements to it. One of those elements is the full model, and the other 15 are various model terms that get left out. And so what we can do is we can evaluate 15 different model terms. Oops. So there's a fair amount of code here. This part's really simple. Let's just create some bootstrap resamples of our data. This part creates a workflow set. It says I'm going to fit, a basic linear regression model. My preprocessors are going to be this list of different formulas. So there's no recipes or anything here. It's just different variations of that full formula. And then I'm just there's no tuning parameters. So I can use the fit resamples model and evaluate all those submodels using the bootstrap. And then I'll calculate, I want to do something different than RMSE, so I'll calculate the mean absolute error here, and then set the seed so it's reproducible. So what we can do, and that's what these final bits do, is they take out all the mean absolute error statistics from all the bootstrap samples and pulls out the full model. And then what we'll do on the next slide is we'll merge those back together. For each resample, we can calculate the difference in the mean absolute error with and without that predictor. So by default, it's just 25 bootstraps. So I have 25 estimates of the performance loss by removing a particular model term. This is a fair amount of like little dplyr type stuff, but what this basically does is it merges those two data sets together, it calculates the loss of performance. So what this is saying is, since the mean absolute error is better when it's smaller, we're taking the estimate where we've removed a model term and subtracting the estimate when we had the full model. So what that means is a positive result here, like a positive value, means that performance got worse when we didn't have a term in the model. And then the rest of this code just aggregates that across all the bootstrap resamples and calculates a confidence interval and plots it. And so the result here is what you see is carbon is really, really important to this particular data set, because if carbon and its interactions are never in the model, we lose a lot of root mean squared error. So our root mean squared error gets worse when this is not in the model, which means it mattered a lot, because if we don't have it in it, our performance kind of stinks. And then you can see the next most important is hydrogen. So you have like some of the main effects here are important. Sulfur and nitrogen don't really matter to this problem at all. And then you can see which of the interactions are important here too. As you can see that the carbon oxygen, carbon hydrogen, and maybe hydrogen oxygen, since they're above 0, indicate that they had some benefit to the model. But you can see which ones you might want to keep and also their relative effect. And honestly, for this particular data set, there's a pretty linear correlation between carbon and the outcome. So you might go back and look at these data and say, oh, actually, like a model with carbon just might be good enough, depending on what your criteria for goodness is. So I might make a function that just automates this and does it for you. But I thought there's a lot of code here that I haven't walked through, but it's basic dplyr code and ggplot code. And just to give you a sense of like, not so much about this code, but like how you might use workflow sets for things that are not like some machine learning type problem. This is almost like it's doing an inference. It's saying like carbon is statistically significant in terms of mean absolute error, because when I don't include it, you know, the offset in performance is larger than basically like the degrees of freedom that can get consumed when it's in the model. So it's just like a slightly different example. And that's pretty much it. I know there's a lot there. Just to summarize, workflow sets can be very helpful when, for one reason or another, you need to fit a lot of different models. It's also useful from an AutoML standpoint to do like a stacking method. And we have some high level, you know, APIs with workflow sets to like, you know, track the models, like which ones worked well. Even if you've already fit models without using workflow sets, you can make sort of like your own after the fact and use their plotting methods and ranking methods to figure out which ones are best. So you don't have to start with workflow sets. You can take your parsnip models and all that and make them into a workflow set. But I don't see this as something that people are going to always use. I don't see this as something that like everybody's always going to be doing in their analysis. It fits like a fairly narrow set of use cases, and therefore I don't think it's like something that is going to be like a household sort of like function, like or package like parsnip or recipes or something like that within tidymodels. So I think it's really good, and it can be very applicable to certain scenarios. But generally speaking, I think this is like it should be used sparingly because you don't need it otherwise.